Well, let's go ahead and get started. So welcome to the March edition of the Northwest Gas Association's monthly webinar series, featuring today Cassie Davidson, Manager of Carbon Management, Fossil Energy Market Sector at PNNL, Pacific Northwest National Labs. We've had great opportunities to work with PNNL over the years. In fact, my dad had ties to PNNL for years, but great organization and real terrific asset that we have here in the Pacific Northwest. And we're really pleased that Cassie could join us today. We hope she'll take a little bit of time to talk about the program actually that she works with, in addition to the presentation that she's going to provide us. As a reminder, folks, we ask you to stay muted to avoid any unnecessary background noise. So you'll be muted for the entire webinar. We ask you to use the chat function to ask questions. So a reminder, when you pose a question for Cassie, here's a reminder for you. I'll just interrupt you at that moment and ask the question. So you don't need to monitor the chat. I'll take care of that for you. And we'll just take questions as they come up. We'll also give you a couple opportunities throughout to pose questions. So give yourself a little bit of time to type them up. And Cassie's graciously said we can make the presentation available after the webinar. In addition, we're recording the webinar today, and that will be posted to our YouTube channel a little bit later today. Finally, just one last reminder, after today's presentation, Judy will circulate a poll to those of you that participated, just gathering your thoughts on what topics and issues you'd like to hear from during our monthly webinar series. So we want to make sure we're bringing content to you that you value, and we appreciate your feedback on and suggestions on what that content might be. So Cassie, I'm going to go ahead and stop sharing, and I think you can go ahead and share your screen now. And let's see, we'll make it work.
All right. Let's make sure. You guys see my screen?
Not yet.
Not yet. How
Okay,
about now?
coming up, there it is. We've got
Perfect. Okay, great. Thank you so much, Dan. I'm going to give you guys a little bit of an overview of what Pacific Northwest National Laboratory is, where we are, what we do. It's surprising sometimes that folks, even here in Tri-Cities, don't know we're in their backyard and sort of conflate us with Hanford. So we always try to give that kind of an overview. And then I do want to get into the meat of this, which is focused on carbon tech and specific regional nuances about how carbon tech, what that means, and what the challenges are for deploying that here in the Pacific Northwest. So I won't be able to see the chat. So thanks, Dan, for calling out any Q&A. And I'll probably spin through a few of these slides pretty quickly. So if there are things that you want me to go back to or discuss in more detail, I'm happy to do that as well. Just throw a note in the chat.
Okay, while Cassie takes a breath, I'll just remind folks, we've had a couple new ones join us. Just a reminder, you'll be muted throughout the webinar. Please use the chat function, either at the bottom or top of your screen, depending on how you're formatted, to submit questions. And I'll be monitoring that throughout, and we'll ask the questions as they come in. So thanks, Cassie, go ahead.
Sure. So my name's Cassie Davidson. I'm a research scientist at PNNL. I've been at PNNL for 20 plus years. As a scientist, my background's in geology. I also went to the dark side and did some hard time in economics. So I live at that place where engineered systems and natural systems meet policy systems, and have enjoyed the variety and interdisciplinary collaboration that comes with living in those spaces. And that is pretty key to clean tech, carbon tech in particular. Right now, there are a lot of integration challenges between the engineering, the science, the policy, and institutional frameworks like markets. So it's been an interesting, sometimes random walk of a career, but have gotten to work with a lot of really cool people. So some of the work that I'm going to be presenting today, much of it is not my own research. I'm talking about stuff across my portfolio. Currently at PNNL, I have the honor of stewarding PNNL's portfolio with the Office of Fossil Energy and Carbon Management, which includes everything from methane emissions mitigation in interstate pipeline distribution systems, all the way to CO2 capture and conversion into things like methanol, and then the stuff that we can't convert, putting it in the ground and understanding what happens to it in the subsurface. So we run the gamut. It's a lot of interdisciplinary work. Let's see if I can get my slide to advance. Okay, so PNNL is one of 17 national laboratories. Some of these are scattered all over the country. PNNL is the kind of on the ground lab here in the Northwest. We also do work in Alaska, but we do work across the country, and there are other labs who also have participation on projects here. So if you recognize any of these other logos, there's probably good reason for that. These are our orbs of awesomeness. I'm not going to go into this too much, but the core of what we do at the National Lab, because we're managed by part of the Department of Energy called the Office of Science, and Office of Science is tasked with focusing on fundamental science. So the fundamental discoveries that become the seed corn for new technologies that will deploy over the years after that discovery is made. So while we have that core mission of scientific discovery, we also have these two missions that pull strongly on that foundational science for sustainable energy and national security. So you can see a little bit the disciplines that we work on here in the second version of that orb. PNNL is one of DOE's most diverse laboratories in terms of our funding structure and the breadth of our mission impact. So we have 5,700 staff. This number continues to astonish me. I was shocked when we cleared 5,000. Now we're at 5,700. We do about $1.3 billion in business, most of that with the U.S. Department of Energy every year. 1,700 plus peer-reviewed publications for scientists. That's kind of our figure of merit. Are we doing things? Are we getting our science out into the greater R&D community so that other people can learn from our discoveries? And the peer-reviewed piece of that is really important, because it's not, we can't just publish something and say we published it. We have to publish it only after our scientific peers have evaluated it and deemed it worthy. So there's an inherent scrub that we go through in publishing our research, and that's critical. In addition to those 1,755 pubs, we also had in fiscal year 2022, 272 invention disclosures, and this varies up to 400, 500 invention disclosures a year. Just like our peer-reviewed publications kind of bounce around between 1,500 and 2,000. But while the science, getting the science out there is measured by our publications, whether or not we are turning those things into technologies that can drive the U.S. economy and DOE's mission, not just in the energy space, but also in the environment space forward. Those invention disclosures then lead to technologies that can be licensed by the private sector and deployed. And then just in terms of our spending, these are the different parts of DOE, the Office of Science that stewards us, energy and environment that since about a quarter of the work that we do every year. National security is a little more than that. And then we have these non-DOE sponsors that account and private industry sponsors that account for just over a quarter of our annual business. And of course, almost everybody who's a scientist at some point was a nerdy kid who loved science. So part of our mission in our communities and in the region is to pass that love of science along and to help grow the next generation of STEM professionals. Okay, so likely preaching to the choir here, but just to motivate this discussion of getting to net zero, we know that the impacts of climate change have arrived. This is from 2021, from Science News, with some record heat events that were happening then. I haven't bothered to update this graphic because we continue to see these events, atmospheric rivers in California. We know that we're seeing shifting climate patterns. So these every 1,000 year events are now every 5 to 10 years, looking forward at a 2 degrees C global warming future. So limiting that, staying below 2 degrees C or at 2 degrees C doesn't prevent us from having to endure the impacts of climate change, but it does hopefully avoid some of the worst ones. Here's similarly a wildfire map from September 2020. The regionality of some of these concerns is evident and has been increasingly evident over the last couple of years. So we're seeing a lot of state-specific policies in this regard around climate and convergence in some states on some consistent policies, but that is all still evolving. This is from a report that CETI did a couple of years ago, these graphics talking about what the future looks like, what getting to net zero CO2 means in the Pacific Northwest. I think this was for Washington State. The conversation that I often get, because I have fossil energy on my business card and carbon management on my business card, is, well, we should just be doing all renewables. And the conversation around carbon management as an enabling technology that, the less we do to create mitigation technologies around fossil fuels, the sooner we'll move to all renewables. And for folks who are functioning in the energy ecosystem, at least in the near term, building more renewables is going to require building more gas so that we can integrate those renewables and provide a stable, reliable grid in the Pacific Northwest. So yes, renewables, and yes, grid assets. And for the near term and probably the midterm, that's going to continue to be natural gas.
Casey?
So I won't spend too much time on that.
Casey, sure. I have a question here. This is my question, actually. So I've seen the analysis in Oregon. I'm not sure what it is in Washington. I'm probably a little less, but maybe not much less. We hear constantly that emissions from buildings are pretty high. In Oregon, they're the second highest contributing sector of emissions behind transportation, at 34% of the state's total budget. And this goes to your comment about needing more gas-fired electricity. When you break that down and look at what makes up that 34%, 6% comes from natural gas combustion in commercial and residential buildings. It's 6.5%. 21% comes from electricity. So the emissions associated with the consumption of electricity is 21% of the state's overall budget. As we load onto that grid, how, we're going to be, I don't know. So isn't that number going to go up? Or, I mean, we've got things like CETA and the Clean Electricity Act in Oregon, but how does that comport? I guess I just thought I'd throw those numbers out. It seems like we're already emitting a lot from the electric system. The bulk, 3 times the emissions from buildings comes from electricity, not natural gas. And so the end use of natural gas seems like quite an efficient way and a low emitting resource compared to electricity, but we're talking about electrifying things. So posing that question, I don't know, that maybe that's a comment more than a question.
Okay, I think I'll take it as a comment, and also comment back to you that I think you're right. There is this push toward building electrification and reducing the amount of direct use natural gas consumption for building heating, and that's electrification is a way of it is put out there as a way of reducing overall emissions, because there is this expectation that the emissions associated with a kilowatt hour of electricity over time will go down. And what concerns me are drawing a straight line and saying we're going to do this by, and not that this is what this analysis did, but we're going to accomplish this by getting rid of all of the gas and replacing 1-to-1 with wind. And the capacity factor of wind and the capacity factor of a baseload gas plant are completely different. So they don't swap 1-to-1. And I think that's, again, I'm preaching to the choir here. You guys know that, but helping folks understand that there's a service that whether it's direct use or but particularly electric production, there's a service that provides that isn't replaced by intermittent renewables. I think there's a lot of interest right now in developing grid scale energy storage. There's a lot of funding going into that. If at some point in the future we get to the point where we can just run entirely intermittent renewables and the hydro system and do everything else with batteries, that would be great. We're not going to get to that in the next 10 to 15 years unless there is some completely disruptive event that brings that about. So if we're going to reduce overall emissions, if we're going to reduce the energy intensity or the carbon intensity of the electricity that we already have on the grid and continue to provide a stable, resilient grid for the Pacific Northwest and also serve new load, the way that we're going to do that, yes, will be with some part renewables. And until we have those magical battery technologies that can come in and completely replace something like a peaking gas plant, we will continue to need peaking gas plants. So part of what I wanted to talk about today is how we square those things. How do we do the new gas resources that we need to be able to integrate the new renewable resources and also drive our carbon intensity vector toward zero. So this is some really nerdy work, and I'm not going to go into it. I can send people the paper if you're interested in it. But back when I did research full time, this was a paper that we did looking at how to get to at the time the Paris Climate Agreement was the thing that everybody was talking about and was relatively recent. So we looked at a couple of different scenarios for getting to a Paris type target for CO2 emissions globally. And everything else is the same. We're all, in both of these cases, you're getting to the same target. In both of these cases, the energy prices are the same, resources are the same, all of the technologies that are available are the same, with one exception. In the top graph, we don't have CCS available in the model, and I'll talk about CCS technology in a couple of minutes. And in the bottom graph, we do have CCS available. Everything else is the same. Still deploy wind, still have nuclear, still have all of the transportation electrification pieces, but without CCS, you end up needing to deploy a lot more nuclear. You're doing some kind of wild things with transportation and driving those costs to zero. When you have CCS available, you still get to the same CO2 emissions, but you do it without having to, a 30%, 37% nuclear generation by 2100. The permitting ramifications of that are mind-boggling. Even 21%, I think, is aspirational. And again, I can send people the paper if you want to go through all of the nerdy details, but the way that this shakes out is that without CCS, to get to a Paris increased ambition target or a Paris 2-degree target, which is the one you were just looking at, the cost of doing it is twice the societal cost of doing it with CCS. All else equal, you still have to get to the same target. And it costs you twice as much if you don't have this technology, because you have to go after much more costly abatement options to get there. So that's why, for me, this is one of the things that drives my interest in these technologies and my desire to understand how they can best fit. There's no silver bullet. I've been saying that for my entire career. I'm now raising young scientists into, they're really excited about the one technology that they're working on, and having to sort of, your technology is awesome and we need it. And we also need all of these other technologies all of your colleagues are working on. So the fact remains, there's still no silver bullet. To that point, PNNL in my portfolio, we're focusing on some big transformational outcomes. We want to demonstrate next generation solvent technologies for CO2 capture to meet this very aggressive $30 a ton levelized cost of capture that DOE has set out there. Currently, we're winning. We're scientists, but we're still competitive, right? We still want to beat everybody else to the finish line. And in this case, we have the lowest cost CO2 capture solvent currently published in the open literature. And I think this seminar invitation to speak to you today came out of some recent press that we had on those technologies. We want to develop geologic CO2 storage here in the Pacific Northwest. I have spoken with companies that wanted to site here in the Northwest, but because we didn't have proven CO2 storage capacity the way that they do in Texas, chose to take their clean tech billions of dollars and do project development in Texas instead of here in Washington or Oregon. So that was one of the clarifying moments for us, that this has gone beyond, here's some cool science that we can do to help future developers understand how this might work, to the future developers are now here and they need to understand this. And so the science that we've done is very relevant in these spaces right now. We've also got artificial intelligence tools, machine learning tools for real-time CO2 injection monitoring. We have a really cool platform where we can capture CO2 and in the capture solvent convert it to other stuff like methanol, which when you take 2 unit processes and you sort of smush them together, you get to save on your thermodynamic transformation costs. So it's cheaper, and that's really cool. And you get a value added product. So that was new science, that an entire field of science that has opened up recently that didn't exist 5 years ago. And it sort of originated here, which is really neat. And then we're doing ecosystem restoration, quantification, measurement, reporting, and verification for CO2 removal technologies, and finding ways to use CO2 capture to make, for example, to take a gas plant that is doing CO2 capture and being able to ramp the capture unit so that the facility looks like it's load following, even though it's continuing to operate at base load, because you're ramping your CO2 capture up and down depending on whether you need those electrons on the grid or not. So briefly, demystifying the technology. For those of you who are not aware, I keep saying CCS or CO2 storage. CCS in general is CO2 capture, where we're taking it out of natural gas power plant flue stream, or a hydrogen facility, or iron and steel, cement, ethanol, or atmospheric air. This is direct air capture. Carbon dioxide removal is very hot in the press right now. DOE is funding it. We just had a funding opportunity close, and we submitted a proposal for a direct air capture hub here in the Pacific Northwest. There's a lot of interest in it, and but it is one of the flavors of CO2 capture that we could be looking at. Then you take the CO2 and you move it to some place, and then you store it in the subsurface. Typically in the mid-continent, this is done in sandstones and limestones. Here in the Pacific Northwest, we have a rock called basalt that has some neat properties that I'll talk about in a minute. So here was some of our recent press on the lowest cost CO2 capture solvent, and also our ability to convert it into methanol. So my colleague Dave Heldebrandt, who is the principal investigator on our CO2 solvent technologies, is holding a vial of methanol that was created through our process, where we took CO2 that was captured off of a flue stream, and in the solvent where it's more reactive, we've converted it into methanol, which can be sold. And this is a technology that we've developed with SoCal Gas. SoCal's not, they're not the developers who would be using this, but they've been great partners in helping us develop technologies that are needed and that help bridge this clean tech gap. And if anybody's interested in any of these papers, we had Clean Technica, CNBC had a great article on not just the solvents, but some of the other work that we're doing to put CO2 in the ground. So let me know. I can send you those things.
Casey, is your contact info going to be at the end of the slide?
It is indeed. And you guys know where to find me as well. I think Judy can find me too.
I do have one request for your CCS paper already, so I'll make sure to. So Sean Hansen, make sure you write down Casey's contact info at the end of the deck so you can ask for that CCS paper. Thanks, Casey.
Yeah, absolutely. So it's been really clear. We've put so much CO2 into the air, and that's gotten sucked into the ocean. There's so much anthropogenic man-made CO2 that's out there. Folks like IPCC, the Intergovernmental Panel on Climate Change, have recognized and been very clear that we will need to do some degree of carbon dioxide removal from those natural systems. And there's a whole suite of things that you can do. You can do enhanced weathering, biochar, forest solutions. We're currently working on a lab call for DOE for measurement, reporting, and verification of some of these technologies so that we can kind of do apples to apples comparison of them. And then there are, of course, the engineered solutions like direct air capture, where you are pulling the CO2 out of atmospheric air, or bioenergy capture. When you grow a plant, it's sucking CO2 out of the atmosphere. And when you do something with that plant to turn it into energy, you can capture the CO2 back and put that in the ground. You've actually just created a net negative credit of some quantity of CO2. So those are the things that we're typically looking at. So and I put this in there because there's clearly some need for carbon dioxide removal, but I'm hearing more and more when I give talks, people saying things like, well, why don't we just do the carbon dioxide removal and not capture the CO2 from these point sources? Because carbon dioxide removal is virtuous and CO2 capture from point sources is industry. And so that's less virtuous. And so I have put together these 2 slides just to kind of talk about why it's important to do both and why CO2 point source capture is still virtuous, even though we're interested in carbon dioxide removal as well. This is a dude named Thomas Sherwood. He was an engineer in the middle of the last century. And Sherwood noticed that when he looked at separations costs for different things that he was trying to get, he noticed that low concentration stuff costs more to separate than high concentration stuff. And that he published a paper on it in 1959. And it turns out that this holds for CO2 as well. So on this graph, we're looking at little orange dots, our cost per ton of CO2 to separate. And then the blue bars are the purity of that CO2, the concentration of CO2 in those streams. So the lowest concentrations give you the highest cost per ton of CO2 to separate. So there's Sherwood looking smug, that, you know, something that was true in 1959 proves to be true here as well for capturing CO2. So even though we need to do all of this, we need to keep CO2, we need to pull some amount of CO2 out of the atmosphere. Keeping it from getting into the atmosphere in the first place is cheaper on a per ton basis, and is also really, really important to do. We can't keep pumping it into the atmosphere and then capturing it at hundreds of dollars per ton once it's there. All right, so this map makes me mad, still makes me mad. This is the from the Great Plains Institute. They put this map together of what the economy-wide carbon capture, transport, and storage system would look like. And you notice that the economy apparently doesn't include anything west of the Rockies or along the East Coast. But to their, in their defense, there really wasn't a lot published on CO2 storage capacity resources along the coasts. And we have in the middle of the continent where there used to be these huge inland seas that left big, thick, clean sandstones that you can store stuff in, the same sandstones that you would get oil and gas out of. We don't have those out here on the coasts, at least not in the kinds of quantities that they do in the middle of the continent. So making sure when I give talks, I try to make sure that folks are aware we have a lot of CO2 point sources on the coasts, and we also have CO2 storage resources, but they are not those oil and gas bearing resources that you see in other parts of the country. I mentioned earlier, we had a company reach out. They wanted to do a clean tech project here in the Northwest, and they chose to go to Texas because they didn't have the certainty here in the Northwest that they would have in Texas for what are they going to do with their CO2. In Texas, they know they can put it in the ground and get rid of it and sell a net negative CO2 product or a net zero CO2 product. Here in the Northwest, we have more complicated geology that hasn't been as well characterized because there is not a significant quantity of oil and gas in it. So all of the information that we have on the geology in Texas came from the oil and gas industry, and they haven't been as interested in the Pacific Northwest for oil and gas for obvious reasons. So we have less data. And then we have, I mentioned earlier, we've got this really cool rock called basalt, and that is present widely in Eastern Washington and Oregon, as well as a bit into Idaho. And that's shown by this gray shaded blob here on the second graphic. Regional strengths and opportunities that we have from a capture perspective, we don't have as many point sources because we have renewable energy, we have the hydro system, so we don't have a large fraction of coal plants like they do in the Illinois Basin, for example. But we have the opportunity of using some of that renewable power. There's a lot of interest in this right now. Could we build renewable power, new developments of wind and solar to run direct air capture, carbon dioxide removal projects? There's obviously a little bit of a mismatch there. Every direct air capture company that you talk to, their capacity factor is 90-95%, and they're going to run on fully renewable. But they'll put in a battery, so it'll be okay. So there's some system level modeling that needs to get done to make sure that those things can be integrated in a way that makes sense for the grid as it exists. And we have a very well parameterized grid here in the Pacific Northwest. So having the opportunity to do some of that modeling, we have opportunities for integrated conversion of CO2. There's a lot of interest in sustainable aviation fuel right now and converting CO2 into those sorts of products. We don't have a lot of natural gas or CO2 pipelines the way that they do in Texas, like the Kinder Morgan pipeline system or the Denbury system in the Gulf. So that is a thing that we would have to address. But we do have opportunities for intermodal transport for smaller volumes, and we have a lot of basalt that could potentially be a storage resource. All right, so we don't have a lot of sedimentary reservoirs like you would in oil and gas country, but we have these really cool basalt rocks. And the take home here is that basalts can convert CO2 into solid minerals, and they can do it very rapidly. I'll talk to you in a minute about a project called Wallula that we did out at the pulp and paper mill. It was Boise at the time, now it's Packing Company of America, to see if the folks that were working in the laboratory were seeing, they were getting these really fast reaction rates, and we wanted to know if that was feasible in the field. The other one of these projects that's been done is and this is super nerdy, there's not going to be a quiz later, but just to kind of put the marker down here, the pure phase CO2 is what we did here at Wallula. And there's also a project called there's a company called CarbFix that has a project in Iceland called Project Orca, where they're taking CO2 that's captured from the air and putting it into these basalt rocks like we have here in the Northwest, and turning it into minerals. The only difference, the main operational difference is that we're putting CO2 in the ground as a pure phase supercritical fluid, and they're doing it as a dissolved gas like soda water. And it causes slightly different chemistries, but ultimately the principles of turning that CO2 into rock are the same. So this, just to give you a sense for how these systems work, this is Palouse Falls on a beautiful spring day when it's not flooding. And if you look at the side of the canyon, you have these very straight-sided rocks, and they're straight-sided because they don't have a lot of holes in them that water can get into and break the rock apart when it freezes. So we call that low permeability, and those flow interiors are kind of our cap rocks. There are barriers to anything we put in there getting out. And then in between where you see the grass growing, that's because that rock is broken apart because it has holes in it and stuff can move through it. So if this was a sandstone, that would be really good sandstone for reservoir rocks. And here that permeable rubbly stuff is our reservoir rock as well. So you have these sequences of a good reservoir and then a cap rock on top of it, and a good reservoir and a cap rock on top of it, as you would have in a sandstone. All right, so if you've ever been out there, that is a terrifying drop. 115 meters from the top of that bluff to the water level in the canyon on a normal day like this. The storage depths that you need are about 7 times that to maintain CO2 as a supercritical fluid. So you need 7 Palouse Falls canyons stacked on top of each other of depth before you can actually put CO2 in the ground. So it's very, very deep. At its maximal thickness, these basalts in the region are about 4,500 meters thick. So we have a lot of potential capacity there. And then our little test at Wallula, we injected 1,000 tons of CO2 in 2013. We shut the well and walked away. It took us about 3 weeks to get it in there. Closed the well, walked away, came back in 2 years and took samples from the reservoir. We did some drilling where you go in and you can drill out a sidewall core and bring it up, and then cut it into very, very thin slices and looked at what was there. We wanted to understand, we did isotopic analysis to understand the whether the CO2 that we had injected was incorporated into any of the minerals that had formed, and found that it was. Those minerals are made of the CO2 that we injected. And it happened really fast. The results that we got after that 2 years of shut-in suggest that we have about 60% of the CO2 that we had injected after 2 years was turned into a mineral. And projecting that out, we're thinking somewhere around 10 years, you've got greater than 90% in mineral form. So this is really exciting for potential project operators, because if you're putting it in the ground in a sandstone and it just stays there, and that's good, we need to do that. But you have to monitor it and you have to make sure, and it's, there's long-term liability is something that people are concerned about. And this means that your long-term liability is 0, because the CO2 that you put in there is now a rock, and rocks don't migrate. Well, they do, but over very, very slow periods of time, riding on continental plates.
Hey, Casey, maybe you mentioned this, but was this the study that was done like around the Port of Walla Walla? Weren't you down there? PNNL did I think it was like 2013 where you guys did some tests in the basalt, right? Is that this
Yes.
one?
Yeah, this was the Wallula pulp mill, which is right there on the water, right between, like, if you're driving from Tri-Cities to Walla Walla, it's right on the way.
So this is the first I've heard that you've seen results from that study, and I guess my implication or my understanding was it was sort of a kind of results, like, and I don't know what the barriers are. Basalt's a very brittle rock, and is it hard to get into it without fracturing? There was oil and gas exploration done around Mattawa, right? Where I think Shell actually came up with new drilling technologies because they had to get through 10,000 feet of basalt. Yep. Am I conflating things here? Or
no, yeah, no, that's exactly the oil and gas exploration that Shell and Arco did in the 80s. Those are some of our key data wells. We know what we know about the subsurface in this area in large part because of those exploration efforts. So whereas in Texas, they have many of those wells, we have a handful of them because of those efforts. It wasn't meh, it was, wow, that's pretty cool. But because you don't get any oil or gas out of the ground when you inject CO2 this way, you don't have that. For a while, that carrot was really important. Before we had 45Q tax credits, before we had strong market incentives and kind of shareholder pressure on companies to do something about their CO2 emissions, the carrot was getting additional oil out of the ground. So from that perspective, this was a little meh. But from the perspective of permanent safe storage, it was really exciting. And funding was cut for reasons that are kind of water under the bridge at this point, but we're finally getting funding from DOE to go back and look at the data that we collected at Wallula. So that's why we've got some recent papers that are coming out, and a lot of interest from industry, from community stakeholders, from regulators in understanding how this works and how it would be permitted. And as you know, in terms of, can this be done at scale? Those are great questions. Those are all things that we're very interested in. There are companies out there right now who are saying, sure, this can be done at scale, and we're going to come out to the Pacific Northwest and we're going to do 100 wells. The science doesn't yet support that. There's still more learning that needs to get done. So this isn't, I've had people call me and try to shake me down, like, you're withholding the perfect well location. I'll write you a check right now. I need to get CO2 in the ground. We're just not de-risked to that point yet, where I can put an X on a map and say, go do this and do it this way, and it'll be great and you'll get all your credits. But there's enough interest right now that I think we have a broad coalition of people who are interested in supporting the work. DOE just announced funding for our HERO project, which is the Hermiston, Oregon calpine plant. We're going to evaluate that geology for CO2 storage at commercial scales. And this will be the first science well we've been able to drill since Wallula. So very exciting. We're hoping to answer some of those questions. There's a lot of demand right now for being able to do this. If we're going to build new gas-fired capacity and also get to net zero, we have to figure out how to do something with the CO2 from those plants. So this is a key piece. We're excited to get to do the science behind it. We've got some really cool partners that we're working with. And speaking of partners, it's been a lot of fun for the old folks here to get to hire some early career scientists who are excited about this. So we're kind of where we can pull people in who have retired since Wallula happened. We're trying to get the band back together a little bit there, but also bringing in this outstanding group of folks who are going to carry this work on. It's been exciting.
That's exciting. Really exciting that there is momentum building behind CO2 storage in the Northwest in these basalt formations. So, I guess I've been vaguely aware that it exists and is a possibility, but like I said, I thought that first Wallula test sort of came back, and your explanation is perfect. I understand that, but there's other incentives now that didn't exist back then that make it more interesting again, right? So that's pretty exciting news. Well, do we have any other questions for Casey? Let me give you just 1 minute to, okay, here we've got a question. Is there basalt underlying Portland General Electric's Carty generation plant in Boardman? Yes.
There is definitely basalt underlying Boardman. Yes.
Yes. Yeah. That was, you saw that big gray blob that Casey put up earlier, and it's pretty much all of, if you think about the what do they call it? Not the scablands, but the Missoula flood area. That's kind of, a lot of that is all where the basalt was, right? And down into Eastern Oregon as well. So yeah. Any other questions for Casey? Well, Casey, that's super exciting news, and we really appreciate your time today. I've made a note to myself, if there's anything to show out there at Calpine, I know that Calpine, we partner with Calpine on some things, and it'd be great to get some legislators out there to get excited about some of these opportunities. And I can work with your government community affairs people and you to, I don't know if there's anything to see out there, but I think it would be a fun field trip and real informative to folks who are really focused on real world solutions. So appreciate your work. Any other one last call for questions? And while you're typing away or waiting to type away, I'll just remind you all that Judy will be sending out a poll asking you for your suggestions on webinar topics you'd like to hear or participate in. So please take just a couple minutes to fill that out, give it some thought. We will, Casey has generously agreed to share her deck with us. And so Judy will send that out after the webinar. In addition, the webinar has been recorded and that will be posted to our YouTube channel here later today. I do have a question here, Casey. So can Casey comment on partnerships with utilities and what utilities should be thinking about in creating them? I think Dave comes from Northwest Natural, so this is from actually specifically a gas utility. But partnerships with utilities, Casey, and how can utilities think about getting into this game?
Excellent. Is that Dave Stanton from Northwest Natural?
Yes, it is.
Hey, Dave. I'm glad you were able to attend. Yes, we love to partner with people, figuring out kind of what you all need, what's going to help make these technologies deploy is important to us. We want to make sure that our science is pointing in the right direction of serving the need that industry has. So we very much value our industry partners, as Dave knows, figuring out kind of how to merge the streams. We're DOE funded, so my job is to go after DOE funding opportunities with partners and making sure that those align with the interests and needs of utilities. You all have a job to do, a day job, and making sure that what we're doing together helps your day job as well as helping us with the research. That's always kind of something that we need to finesse. But DOE is putting funding opportunities out there all the time. So if you see something that you're interested in, even if it's not in my space, send me a note and I can get you connected to the right folks at PNNL who can talk to you about getting plugged in on those things.
Okay. All right. I think that's it. Casey, thank you for your time. And